Hello again. We are going to continue now, and in this part we are going to consider the design of a lead controller using a body plot. And we're going to consider an example. The example here we have transfer function g of s, and let's first look at the transfer function and try to understand it. So if we look at the part here, this is just simplified, and so it shows that the gain is 20. This should be represented by the intersection in decibel at omega equals 1. So this point really should be in decibel, that's 20 log 20, which indeed, if you look at it, you will find it's about 26 decibel. Now, at omega equals 1, the slope is minus 20 decibel per decade. That means we have actually a free integrator, which we do. Then at this point, if that's 1, that's 10, so that's omega equals 2. There is a corner frequency, and at omega equals 2, we have the slope changes from minus 20 to minus 40. And indeed, we have here a pole at 1 over 0.5, which is omega equals 2. So that's correct. Now, the specification is, what we're trying to design is we are going to, normally we have a specified phase margin. Phase margin is related to the damping coefficient of the system, and basically the phase margin in degrees divided by 100, that will gives you the damping coefficient. And the specification required is we design the spec phase margin between 45 and 55 degrees. The phase margin is how far are we from the minus 180. So we look at the system, and basically at this point we need to find the phase of GS and subtract that from 180. Well, we can do that. We can do that indeed by looking, that's our GS. If we can say substitute instead of S, put j omega, and then put omega equals up from the sketch here, that's not very accurate, it's about 7, then you can find the phase margin, and I will leave that to you to do. And assuming that omega equals 7, you will get the phase of GS equals minus 164 degrees. Minus 164 is still less than minus 180. So the system is stable. But by how much? 180 minus 164, it will give you phase margin. Assuming this omega, phase margin will be 16 degrees. That's not sufficient. Do I really need to calculate it? Well, let's think. A free integrator here will give me a phase of minus 90, and it's constant. A pole at this point, the pole will give me at the corner frequency minus 45 degrees. So at this point here at omega equals 2, I estimate that the phase phi of G of S is minus 135. And then the contribution to the second pole will start to increase. So as we move this way, it will start to increase. So somewhere here, phase margin could, well, the phase phi could be 150. 150 minus 150, which means the phase margin would be only 30 degrees. Just estimation. It's not actually. If we calculate it, it will be about 16 degrees. Anyway, that's way smaller than the specification. So how can I adjust the system? I need to add a controller. I know that the second pull here added to the minus 90. Minus 90 I cannot do anything about. I have to accept it. So what I will need to do is to try to change the slope when we cross the 0 decibel line. This is the horizontal line of the 0 decibel line, at a slope of minus 20 decibel per decade. How can we do that? I'll just tidy up this a bit. We can do that by adding a 0, and indeed I'm going to add a 0. If I add a 0, 1 plus taf z, the 0 time constant, multiplied by s, at somewhere here, before the crossover frequency, obviously, because if you wanted to change it. So I chose frequency as 5, added this. Let me just delete this. And then here you can see the gain has increased from the solid black line by addition of the green line, the green 0. I add another pole at this point here. So the slope, the brown slope here will be minus 40. And the green slope here is minus 20 decibel per decade. You can see that the crossover frequency changed, and this crossover frequency, we'll call it omega phase margin, the desired phase margin. So, okay, graphically I showed you what I can do. Analytically, how can you do it? Well, when you gain experience and the confidence, you can straight away go to CSU tool and add a 0 before this original crossover frequency, add a pole after it, and just try by to adjust the location to get the desired response of the system. However, we are going to give a step-by-step in this talk, step-by-step that instruction, how can you design the controller. And the first thing is we establish, well, actually there is a step before that. Well, anyway, the format of the C lead, the lead controller, will be the green 0 over the brown pole, and there is a coefficient here, and of course veta is less than 1, i.e. in the S domain you have the 0, then the pole. This is the lead compensator. And you need to note, without doing any analysis, from what we did graphically here, you can see that when we moved from this curve to this curve to this line, we have an increased additional gain at high frequency. At this point, the gain here was this, minus something like 20. Now with the compensator in, the gain is minus half that. So it's the lead controller introduces additional gain at high frequency. Just an observation. Step-by-step design, what we need to find. I need to find taf and veta. If I find taf and veta, I can design the compensator. And I give here you 8 steps, actually there are 7. The first one is related to the steady state error. The steady state error was covered in the first talk when I discussed how to calculate the steady state error to a number of test signals. We start the lead controller design from step 2. You plot the body diagram of the given system, and establish what is the phase margin without compensation, what is the specification phase margin, and that will give you an idea of how much improvement you need to add to the phase of the system. This, we call this phi m. That's what you need to introduce. Then you can calculate veta from this equation. And you know that the lead compensator will introduce an increase of gain at high frequency. What we are interested in specifically is how much the gain is increased at the new crossover frequency. So you find the value of the increase of the gain, and then you can, from the body diagram, find the new crossover frequency. Then you calculate the first taf from this equation, and you have veta from this equation. You have your controller. Once you have a controller, this is an initial design of the controller. You go to CISO tool, examine the operation. Does this controller actually yield the desired phase margin or not? So I'm not going to keep these steps ahead of you. I'm just going to refer to them as we solve the example. So the first step, step number 2 in the list, is for the given transfer function, plot body diagram and tell us that the phase margin is only 18 degrees. If the phase margin is 18 degrees, and of course you remember the approximate sketch showed us the crossover frequency was around 7. Actually the crossover frequency for the exact diagram is less, so that's why the phase margin is less. Now the first step is current phase margin is 18. We need to improve it to between 45 and 55. I'll use 55. So if that's the spec, then I will need to buy phi m 37 degrees. From phi m, I can calculate veta. Veta is 0.25. What is veta? Is the ratio between the derivative time constant and the integral time constant. Well, actually the opposite. It's the integral time constant over the derivative time constant. So calculated veta, so far simple. Then after that, I just refer to the paper, calculate the gain increase introduced by the compensator from 20 log 1 over veta. That will give you 12 decibel, which means my compensator is going to shift this blue curve here up by 12 decibel, and I need to find the frequency at which the gain is minus 12 decibel, because if that's here minus 12 decibel, if that's minus 12, it's all approximate, but you will fine tune it in CISO tool. If that's minus 12, I need to make this there. I need to move this point there. I need to have a 0 somewhere here to go there, and then we'll go there. So I need to go up 12 decibel. So at this point, when the gain is minus 12 decibel, when I add 12 decibel, that will be my crossover frequency. And the crossover frequency, let me just delete what I added in red. So this is the gain introduced by the compensator. The frequency at this is around 12 radian per second. This is 10 here, this is 10, and this is 100. So this is 20. If that's 10 and that's 20, then it's about 12, 13. Doesn't matter, because you will fine tune it in the CISO tool. So we found this is our omega PM. Then we can find TAF from Vita and the new crossover frequency. That gave us 0.67 second. And you end up with, this is TAF and this is Vita TAF. This is the compensator. This is the first to go at the design, following the steps given in the previous slide. Now we go to CISO tool, and what I did here, I went to CISO tool. There will be a tutorial on CISO tool, and I added a 0 and a pull. Note that I'll just change the color of the pen to black because I don't want to interfere with the root locus. First of all, this is the 0, the pole at 0 and the pole at -2. These are the poles of the process. Then we added the 0 of the compensator, and then here is the pole of the compensator. So you know, you will know if you don't, when you follow the CISO tool tutorial. I added this compensator. It gives you my compensator here, and it shows that the phase margin is already improved. And note that the crossover frequency is increased, which we expect from the discussion that we had at the top of the presentation. Now I can fine-tune things. If I want to fine-tune, I have to understand what I'm doing. We know from root locus that the 0 will attract the branches and the pull will repel the branches. If I move the 0 to the right, it will attract the branches more. Then this point will become here and this point will become there. That will be the new pull. Note that the damping coefficient zeta will change from this to that. Actually, the damping coefficient is going to increase, and if the damping coefficient increases, and we know this is phase margin in degrees over 100, then the phase margin will increase. So if I move the 0 to the right, it will pull the branches of the root locus and make them bend even sharper, and that will affect the phase margin and zeta. How can we understand it? We know what will happen to the damping coefficient, and the phase margin changes consequently. So what we're going to show is I will change the real 0. It was at minus 5.99 minus 6. So I will change it to minus 5. So minus 5, that means it became to the right a bit. If it came to the right a bit, you can see that both the phase margin and the damping coefficient will increase, yes. So that's, the system is more damped than the previous one. This shows how you design. You follow the steps to design, to have an initial design of your compensator. After that, you go to CISO tool and fine-tune it. Next time, we are going to discuss the lag compensator. See you then.